So if different methods for solving the same equations can yield different times, how do we quantify this in a useful manner? We're going to consider solving the value of pi two different ways. The first of these is a Monte Carlo, or a random method. We're going to compare this to a series solution. You're going to implement this in a slightly different form in the homework. Essentially what this method does is it randomly casts a bunch of points into a unit square, and then it separates out those that fall within a certain radius of the center, and it uses that ratio to define an estimate for pi. As you can imagine, this is not terribly efficient of a method, but we can quantify just how good or bad this method is. The second technique we'll see is to use a series to calculate the value of pi to n figures of accuracy, just like we saw a moment ago with the exponential. First, the Monte Carlo code. This function accepts a value n for n degrees of accuracy. It initializes its values, and then it's going to loop until a desired number of significant figures after the decimal place have been calculated. It's a little bit complicated of a code, but I'd like you to go through it line by line and be comfortable understanding what is happening in each piece of this. How are x and y being selected? How are we enforcing that they're inside of that inner circle and therefore being able to calculate the value of pi? Take a closer look at this. It'll help you out in the homework. If I run this, you can see that asking for 4 decimals of accuracy in pi, 3.141, then the 6 is a rounding error still. If we keep going up, MC pi 5, it grinds on it for a few seconds. Let's compare this to the series solution. Series pi, as we increment, tends to be very consistent. It doesn't wander around a lot like the Monte Carlo method was. If you run the Monte Carlo method a few times, you'll find that it varies a lot in the efficiency. In this case, to 4, 5, 6 figures, it's not a big deal. When we start asking for the 7th figure, it takes a while longer. And for each additional degree of accuracy that we ask for, it's going to take longer and longer to reach that. One has to be careful, however, to compare apples to apples. Two codes that calculate the exact same value in many ways may not be directly comparable. So in this case, both of these codes ask for the same number of digits, n, after the decimal place. So we consider them to be comparable. Now there's a tool we can use to actually quantify the values here. It's called %timeit. It's available in IPython and in Jupyter. And what you give it is a function call, and it will run that function call again and again until it achieves an accurate estimate of how long it takes. So in this case, 406 milliseconds, plus or minus 471 milliseconds per loop out of 7 runs. So a lot of variation, which makes sense. This is a random method after all. If we ask it for series pi, in this case it takes 90.7 milliseconds, but it runs 7 runs, but it runs 10 loops each per run. So timeit is flexible. It's going to run it once, and then it's going to decide based on how long that took, how many times it needs to run it to give you an accurate statistical measure of how fast something is. So here we can see that on average, series method is about 5 times as fast as the random method for a given accuracy. And this will change as you increase the accuracy here. Another calculation we can compare is the Fibonacci sequence. This is a set of numbers, 1 followed by 1, followed by 2, followed by 3, followed by 5, etc., wherein each value is the sum of the 2 preceding numbers. We write this sequence generally as fn equals fn minus 1 plus fn minus 2, and start the sequence with the numbers 1 at positions 1 and 2. This gives us what is called a recursive formula because it refers back to itself. If you want to calculate F17, you have to know the values F16 and F15. And to calculate each of those, you have to know the foregoing values as well. Somewhat unintuitively, there's also an analytical expression for the nth term of the Fibonacci sequence that's been discovered. This analytical expression has the advantage of not requiring one to calculate the foregoing numbers. So we expect it to be faster in some cases because you don't have to calculate all of those values. Let's take a look at this in code. Here we've defined fib r as the recursive definition and fib a as the analytical definition. If we invoke fib r for the 6th Fibonacci number, it's pretty fast. If we go to the 16th, again, pretty fast. If we go to the 30th, it takes a moment. It has to think about it. If we go to the 35th, you'll notice that it's going to grind for a few more seconds. And this is true of the recursive sequence in general. If you look at it, because it's dependent on the two preceding numbers, which in turn are dependent each on their own two preceding numbers, we end up with an exploding tower of values that we need to calculate for large numbers. In contrast, the analytical solution is more difficult to calculate for small values, but less difficult for large values. For 6, for 16, for 30, for 35, for 60. I don't recommend trying 60 with the recursive solution. For 120, right? These are large values, but the analytical solution is able to handle them very cleanly and conveniently. Let's try timing these. First, the analytical solution for the 12th Fibonacci number. It's going to run it a few times, and then it's going to give us that result. So in this case, 617 nanoseconds. We run it again with the recursive solution, and we see 42.3 microseconds. So this is a couple of orders of magnitude larger than the analytical solution. If we calculate these values for different Fibonacci sequence numbers across the x-axis and different times across the y-axis, we can see that for small values, the recursive solution is more efficient. But for large values, the recursive solution becomes vastly more expensive. Note that the y-axis is logarithmic. The analytical solution, in contrast, tends to be pretty consistent in how expensive it is. There's a few bumps in it. We expect to see that with timing due to background operating system processes. But on the whole, the analytical solution is very reliable here. So when you think about how to implement a particular algorithm, this is something that you need to keep in mind.